Okay, good morning everybody. I hope everybody's having a wonderful day. So today we're going to be talking more about hashing. Now I just want to remind you of the big picture, like the big picture of what we want to do with our hash table. So remember that the whole idea here is that we're going to store our dictionary in this hash table where we have, remember, our key value pairs. And the whole idea is that we have this thing we call the hash function last day, which uses the hash code. And when we map that to some position in the table. So we last day talked about how we can come up with a hash code, or at least a good one. And then now we're at this point where, okay, the last piece we're missing is what to do with this scenario. So remember, just I want to remind you. Reminder, remember the big thing that we still have not resolved yet is, remember, if I have a hash table like this, and if I give you, say, two records, like with two different IDs, like ID1 and ID2, if I give it to the hash function, suppose I give the first one over and I put that right here, and I give you the second one I want to insert it, it gives me the same location. We call this a collision, right? And I haven't told you anything about what we're going to do with this. So this is what today's lecture is going to be about. Is how we're going to resolve these collisions. Is that clear, everybody? Because once we know how to resolve the collisions, assuming that we do this carefully and do it in such a way that we avoid as many of these collisions as we can, or at least we could try to do that, we'll try to obtain faster lookup times. Because remember, the whole intuition behind this is, remember, if you imagine this table, like if I could just literally stack each collision on almost like a linked list, just like our linked list implementation of a dictionary. In the worst case, I'll have to go through all of the records, right? Regardless, I'll have to. I would like to try to get it so that I don't have to go through as many records as I can. So we're going to see that there's at least a few different ways we could try to do this. I'm going to start off with the one that's most intuitive to the one, at least I think it's the most intuitive one, to what I just described. So the first collision resolution policy I'm going to give you is something we call separate chaining. So let's talk about that. So we're going to talk about separate chaining. So the idea of separate chaining is fairly simple. So here's what the collision resolution is. So if ever I have a collision, the idea is as follows. If a collision occurs, use more memory. That's really the basics of the idea. So, here's the idea. Treat each entry or slot, treat each entry of hash table T as a linked list. As a linked list with node references. So we're just going to have a linked list that consists of nodes, right? So here's the thing. Do you remember what we did when we tried to do like insertions and searching and removing from a dictionary that was based on an unordered linked list? Remember, all I did was I would traverse through the linked list, right? Very often that's what the algorithms would end up doing, is I try to find where it goes, or if it already exists, I want to know it's there. Then I insert appropriately. So the only wrinkle to this whole idea is where I put it. And that's where the hash function comes in. So to get data with key k, hash using, so we're going to hash using the hash function h of k. The data will be in the list. it'll be in the list T sub h of k. So remember, h of k is our hash function given the key k. It gives us a position. We use this position index into the hash table. The hash table now consists of linked lists. So it's actually an array of linked lists, just to be very clear. So let me do an example of what this would look like. So just before I draw the picture, I just want to remind you the whole idea. So remember, the intuition, just keep this in the back of your mind, is that if I have my friends, and I want to, imagine these are seats at a theater, for example. I want to be able to have it so I can quickly identify where I can put my friends in these seats. So I could put like this cute kitty over here, I could put that in that seat. I have my seal friend, I could put them there. I would like to have it some way that it's so that there is no collisions happening. But as we're going to see, that that's something that's going to be a little bit trickier to pull off. So we're going to be presuming that we have a good enough hash function that gives us this uniformity type of assumption where it either practically meets it or theoretically truly meets it. So the whole idea is that if ever I run into a collision in this separate chaining, the idea is instead of it being where, oh yeah, well, what do I do if I have a collision? I'm just going to stack my friends on top of each other. So if I have a collision, like I'll just stack them on top of the kitty here. So this is how I will actually deal with things in separate chaining. Is that whenever I have a collision, I'm just going to put them in the same slot. Does everybody understand the main idea? Except all I'm going to do is maintain this using a linked list, because as we see in the previous lecture, it was something like that. The idea was that when we order or unorder the linked list, it doesn't make much of a difference on the worst case time complexities. Because remember, at the end of the day, if I do insertions, I have to go through all those records anyways in that list to check for duplicates. But the catch with this is that whenever I have a record that I would like to put in, it has the same key, it'll be in the same list, right? So it means that if I have a really short list, when I use this hashing idea, it'll send me to the right list that has it if there's a duplicate. So I don't have to do anything where I have to scan through everything. I could just go to the very specific list I need. So that's going to be the idea here. So let me draw you a picture of what this might look like, and we'll go through some insertions into it. So I'm going to start off with with our table here. I'm going to draw a table that has 7 slots in it. 1, 2, 3, 4, 5, 6, 7. I cheated there. 1, 2, 3, 4, 5, 6, 7. I have to make sure I'm counting them right. It's a Monday, right? 5. I kid, of course, but anyways, all of these are going to start off as null. So when I initially create the hash table, I would scan through all of the slots and assign them to be null pointer at the beginning, if I'm setting them up like this. Keep in mind, you can take this idea and specialize it even further. So suppose I have some records like this. Say if I have 20, let me list them out right here. I'm going to have 21 with a value of 1. Like I have 21 V1. I'm going to have 13 V2. I have 12 V3. I'm going to have 7 V4 and 3 V5. And the hash function I'm going to use is as follows. This is going to be the hash function. H of k is going to be k mod 7. So remember, mod is just integer remainder. So we're going to walk us through this by trying to put each one of these records in, starting from the top, working my way down into this hash table. So first thing, 21 divides 7, right? So because it's 3 times 7 is 21, right? So you know it's going to be right here in the very first slot. So when I want to put it in, what I'll do is I'll access T sub h of k to find the pointer. So if it's null, then I'm just going to simply just put it right. I'm going to create a new node and make that like the head of the linked list. So you can imagine these all as pointers to heads of linked lists. So I'm just going to create a new node. So I create a new node. I'm going to point. So I'm going to assign this particular slot to be this node, because that's just the head. And that's how I would insert this in. But you'll notice that whenever I have a collision occur, I'm going to have to, of course, make sure I go through the linked list to make sure I don't have a duplicate there. Does everybody see that? So let's do another one. Let's go 13. Now 13 is one less than 14, right? So you know that, because 7 times 2 is 14. So that would be sitting right here if it was 14. So 13 is one less, so it's going to be right here at the bottom. So I'm going to now put in 13 right here. 13 v2. No. So I've done the insertion of those first two. Now we got 12. Well, 12 is one less than 13, so you know it's going to go right here. So I create a new node. I put in 12 v3. Null. And then next we got 7. Now 7, notice that 7 would, which slot does 7 go into? Which position? It goes into 0, exactly, because 7 is a multiple of 7, right? It cleanly divides it. So now the way I would go about this is I would first, because I want to make sure I go through all of the records in that list, I would have to traverse this to make sure I don't have a 7 already. Since I don't see a 7 here, I'm going to insert it at the end of the linked list, seeing as I already have access to that already. So I'm going to put 7 right here. That's v4. And I must note that technically speaking, it doesn't matter if it's at the front or the end or the tail of the linked list in this process, but for the sake of convenience, I'm always just going to put it at the end. So next, let's do the next one. So we have 3. So 3 mod 7 is just 3, right? We don't have it big enough to be some multiple subtracting off a bit. It's just 3. So I got 3. I have v5. That v is sort of suspiciously melting. But notice here, does everybody get the idea? All I'm doing now is I just figure out which spot in the table I'm going to insert into a linked list, but I have to traverse the linked list first. So I just insert it at the rear if I'm successful. If I run into a duplicate, then that's when I report an error. Likewise, if I need to do a removal, I can use the hash function to tell me where it is, and I can just traverse through the linked list, delete that node from the linked list, just as you would expect. So notice that all it is just one step above just a linked list. It's just an array of linked lists. Are there any questions about this? This is just the main idea of separate chaining. And keep in mind, we can always specialize this idea further if we know more information about our dictionary. So I'll be showing you in a short moment the get algorithm, so the algorithm for get here shortly, just so you get an example of what this would look like. But remember, the whole idea is that you use the hash function to tell you a slot. So imagine it indexes into 0. Then just ignore everything else. It's just the head of a linked list, and you're just traversing a linked list, right? It's no different than a couple of lectures ago. Is that amazing? So it's a very simple but effective idea. So if there aren't any actually, give me 2 thumbs up if we're doing okay so far. Because if you understand this, you understand separate chaining. How come 21 and 7 are in the same slot? Because 21 and 7 are both multiples of 7. So when I give you a number that is a multiple of 7 and I apply mod 7, it should come out as 0. Yes, yes. So keep in mind that collisions can still happen. Like, this does not guarantee that it's going to uniformly spread it. This is an assumption we're making about the hash function and its behavior. But the idea would be that if ever a collision happens, I can extend this linked list as long as I need it to be. So let's talk about the get operation. So let's go over here. So as I mentioned, put and remove are just like doing insertions and removals in linked lists, akin to our dictionary implementation from a couple lectures ago. So remember, the whole idea is that you have to go through the entire list just to check if there's a duplicate. That's the catch here. You can't just insert it at the front and just say, I'm going to wash my hands of this. I don't have to do anything more. It's just a big old one operation. Now you got to go through the list just in case, because remember, our dictionary requires that every record has a unique key. So anyways, remember, the whole idea is we index into this table at a given spot that's given to us by the hash function. So you'll find that most of these algorithms, the beginning of them is just figuring out which index do we use. And in this case, I'm getting the pointer to what would be akin to us as the head of the linked list. So here's the get algorithm. I give you a key k, and it gives me back the data for key k, or null if this record doesn't simply exist in the table. So I start off by indexing into the hash table using this hash function h of k. You can think of this just as hash function from previous lecture. So you know when we did that variant of Horner's method and I came up with that algorithm there, that's what you could use for h of k, for example. Let's see, if remainder is 1, then the entry will be at the bottom. If the remainder is 1, then it will be actually slot number 1 here. So index 1. So if the number mod 7 is equal to 1, you'll be indexing right here. If it's, say, 1 less than 7, say 6, you'll be right here at the bottom. But yeah, just for those that maybe haven't seen mod so much, let me just give you an example of me just walking through a bunch of numbers, mod 7. So I'm just going to use the percentage because that's the one you'd use in C++. 0 mod 7 is just 0. 1 mod 7 is just 1. 2 mod 7 is 2. You keep doing this until you get to 7 mod 7. And then that's 0. 8 mod 7 is 1. And this repeats forever. This is an example of a periodic function. So notice that it has a period. Notice that if I go up to 0 to 6, there's a period length of 7. For those that are interested in number theory, that's the jargon you would use to describe this function. But that's not really the focus. The point here is that this mod operator actually will wrap around the table. That's what we need to know about for us. So that's why I'm using this rather simple function for us, because all of our examples, it keeps things a little bit easier for us to play around with. So I start off with getting the head of that linked list, and then I just simply am going to traverse it. While this is not null, meaning that, remember we talked actually, before class started, somebody was asking about traversing a linked list. We're using that idea right here. So I'm just going to check if P is not null. If it is null, then we know we've went past the end of the linked list, right? And we find that when we get the key, it's not equal to k. That means I have to go to the next node. So I just assign P to be the next node. And I just repeatedly do this over and over again. This is just traversing through the linked list. So after you're done this, you're either going to have one of two possibilities happen. Either it's going to invalidate this first condition, meaning that P is equal to null, or it will be that when I get the key of the node P, it is equal to K. There's only two possibilities here for leaving this while loop. So if that is the case, if P is null, then you know you didn't find it. You went way off the end. Otherwise, you can get its data because you got a match. And so this is the algorithm that would work for get. So this is us using these linked lists, and all it is just traversing a linked list. Are there any questions about this algorithm before we analyze it? Seems kind of, it seems pretty nice, right? Like it's pretty elementary for us, at least at this stage, because we've seen linked lists before. So the question is, what do we do with that? I'm just using more linked lists. Just like I was talking about the other day with our intuition was try to make these lists shorter. This is exactly that idea. So let's talk about how we would analyze this then. So the first thing that you should notice is that I'm using this hash function. Well, indexing into an array, but computing this hash function under our assumptions, this all takes big O of 1 right here in the worst case. Keep in mind that in the worst case, it will be when would it be the worst case here? It's just like the example I gave the other lecture. What would it be? What would be a worst case scenario for this? So I know right away this first line is going to take me constant time. But what about the rest? Yeah, you reach the end of the list. So for example, I failed to find the record, right? So it means I have to go through the entire list at that one slot. So let's talk about this then. So notice that in that scenario, well, look at this. So everything after here, this all takes some constant number of operations, right? So I don't know, I'm going to call this, well, we know this takes big O of 1 time. Keep in mind I can give constants to all of these. In fact, I'll do that just for the sake of consistency. I'll call that C1, I'll call this C2, and we'll call everything that's inside of the while loop here, we'll call that C3. So naturally, the question is, okay, so how many times is this, how many iterations happen here? Well, as suggested in the chat, it's based on the length of the list, right? So this is C3 times, so I'll say length of list right here. C3 times length of the list. So if I put this all together, I should get something that looks like this. So if I count up all the operations, the time complexity will look like this. It'll be C1 plus I guess it's C2 here, plus C3 times the length of the list. Well, I have a question for you. How long can the list get? It seems like this length of the list plays a very big role in this analysis. How long can the list be? Just think in the worst case. Just think of how long the list can be. And I gave you a hint at the beginning of lecture. So if it makes it more explicit, imagine I give you a really bad hash function. Well, it's not M, M is the size of the table. That is a good guess though. It's a parameter like M. There's another one. So let me just give you an idea for those that are thinking about this. Okay, suppose that I gave you a list of records, say for this example, suppose that all of them are multiples of 7. What would happen in that case? What would happen? Well, if it goes through all of the like if I put like a whole bunch of multiples of 7 in there, but suppose that that's only the records I put in. Like suppose all of the records, their keys are multiples of 7. All of them. Where are they all going? Are they going to be spread out like this, sort of? Or are they going to be somewhere else? Like what's going to happen? I want you to think back to a couple of lectures ago, what I described in the worst case scenario there. Akin to what I was mentioning earlier. what would happen? Where do all the records go? Do they go down here? Is it going to be spread out? Is it going to be congregated in one slot? What's going to happen? If they all have multiples of 7, like I mentioned when we were actually talking about, somebody brought this up. It was a very good question. Notice that whenever I give you a multiple of 7, they all go to 0. Exactly. Very good observation. So notice that it goes to the same slot, all of them. That means that in the very worst case, they're all going to go to the same list. But what does that mean in the worst case? What is that in terms of big O? For this algorithm. So the length of the list in the worst case is what in terms of big O? In fact, you can see it exactly too. Yeah, it's n. Exactly. So the worst case is big O of n. Remember? So all keys may get hashed to the same slot. Right? And that can happen. That is something that can happen. So this is one thing you have to keep in mind, that the worst case is still big O of n. It's still big O of n. However, I want to give you back this intuition that we were talking about with my friends over here, where I was spreading them out uniformly like I'm spreading a butter knife over a very long piece of bread, for example. If I were doing that, and imagine that I was able to have a good hash function that was capable of uniformly spreading the keys across the entire table, on average, what I should expect to happen is that all of them are going to go into spots without colliding roughly with each other. Roughly. So, using this intuition, you can expect, on average, under our assumptions, so on average, so the average case is big O of 1. So I'm going to talk more about that in one moment, but are these two clear for everybody? So remember, in the worst case, it could be that they all all of our records go hashed to the exact same slot. So one main drawback I want to just make you aware of when it comes to separate chaining is it uses, sometimes, depending on what your application is, it may use a lot more memory than you would like to use. So a main drawback of it is using too much memory. So let me make a note about that. So I want to talk about one other concept that's going to be relevant for how I came about with that average case idea. And it'll give you also an intuition for how, practically speaking, you should size the table. So you know how I told you that there's different things we have to take into consideration with our hash table. So for example, we talked about the collision resolution. The next thing, of course, is how big should I make the table? I want to give you some insight into how we might do this from a practical level. And it also actually connects up deeply with this average case idea. So just I want to mention a drawback of this approach, because there's other ways that we could do this, is that it may use too much memory. Because remember, whenever a collision happens, we're at the mercy of how many collisions exactly happen. We're at the complete mercy of that. I would like to have other ways to do it, so I just use the table as I've allocated it. So if I wanted to have M slots, it's going to have M slots. There's no other stuff happening. We're going to see some ways of doing this with such a scheme in mind in a moment. So I want to talk about one other thing just before we get there. So just to summarize, with separate chaining, so get, put, and remove, with all three of these, the worst case and the average case, you get big O of n for put and remove as well, by very similar reasons. And the average case is big O of 1 for all of these, by the same reasoning I gave just a moment ago. So that's wonderful, right? In the average case, presuming that I have the right setup for our assumptions, like I have a good hash function, it's able to uniformly spread the keys across the entire table. On average, what I should expect this behavior to give me is that it should be like that. It's like almost like perfectly placing them in so there's no collisions or very few of them. So let me go into that a little bit further. I want to define something called a load factor. So this is actually something you can think of almost like a constant that you can adjust with the size of your table. It has practical, like there are people that will study this load factor and think about how they might adjust their collision resolution policy or which one might be ideal depending on what this so-called load factor is. So let me define this for you. So alpha, the load factor, is just n, the number of elements in the table, over capital M, the size of the table. That's what load factor is. So if we assume, so typically in a lot of hashing applications, you'll usually assume that M is less than or equal to capital M. Often N is less than or equal to capital M. But in separate chaining, you can have N greater than capital M. So I want to give you just a quick little intuition with this thing. So if N is less than or equal to M, the whole idea is that if it uniformly spreads across the hash table with our uniformity assumption, on average you'd expect it takes constant time to do this. Likewise, if I have it where now N can be bigger than M, that means there's more records than there are slots in the table. I want to give you an intuition for how the average case time complexity gets affected by this. So very often you'll think of this alpha like a constant. In fact, in the way we do our analysis, it is a constant. So I want you to imagine I have my slots in my table. On average, what I should expect to happen is that when I perform insertions into this table, that they should be uniformly spread such that I get something that's roughly this when I fill up the table. Then, if I start having to get collisions happening, what happens is then it fills up a next slot. Sorry, it fills up another record into that slot because a collision happens. On average, what would happen is you would have it where now they're going to sort of stack on each other. But you got to look at it like if I took this and flipped it sideways, you would imagine it's just me adding another node into each one of these linked lists. So notice here, notice that if you take this idea, that it's based on the number of elements it takes to traverse the linked list. But on average, under the uniformity assumptions we have, the length of this can be no more than 1 plus alpha. Can be no more than this. I keep the 1 there because you're going to have it at some point that you're going to have at least one node in these things, at most. Sorry, at most you're going to have one element in there. So what's going to happen is as the load factor changes, if it becomes greater than 1, what will happen is they start stacking on each other like this, where each one of these you can imagine like a slot where each one is the linked list. So that means that in this case, so if so, the average time to traverse a list is big O of 1 plus alpha. So you might ask, Dan, why do we care that this alpha thing exists? Okay, this gives you some insight in how you should size the hash table. So think about it. If you know how many records you're going to have in this table, if you want to have it, say, have some constant number of collisions happen roughly, at least on average, what you should have is that the number of table slots is at least proportional to the number of elements you want to have in the table by some constant. So if the number of table slots is at least proportional to the number of elements, by some constant. For some reason I wrote sum twice. By some constant. I'm sorry, I'm getting very excited about this. By some constant. By some constant. Then, this is where the trick comes in. Then, if you know that these are proportional by some constant, then you know that alpha is equal to, remember, n over m, like this. The load factor is this, right? But if you say it's bounded by at most a constant, this means that this is big O of 1, right? So you could just imagine it like the number of elements or the table size. You can think of it like there's some constant multiple somewhere in here. But the point is that this becomes some constant. And the thing is, we like it if it was a constant because this alpha then is another constant, right? And that's how I mentioned you might want to think about the load factor. So you want to think of it like it's some measurement you would like to ideally match. So you might ask, okay, so what's the practical implication of this? So if you make it so that it's like this, the average case is always going to be big O of 1. That's the big thing. Second thing is it also gives you a hindsight into how you can improve the performance if the performance starts to degrade for your hash table. So if you find that every time you're doing more of these insertions, it exceeds your constant. So for example, this constant amount that it's being proportional by, if it starts getting too many elements or too many records are in your table, then what you need to do is you need to rehash the entire table with a new constant in mind. But keep in mind, here's the thing. You don't have to really have a new constant. You just make the table bigger. So instead of having it where you have this table, it's full. Remember, the one way you can always drop the load factor is by increasing capital M, right? So you don't need to change the constant. You just need to change the table size, right? So if performance degrades, increase the size of the table. Size of the table. And rehash all the records. So let me elaborate on what I mean by this. So you know how I have my hash table, right? It has all the records in there. Okay. You know how when we copy elements to a new array, right? Like what we do is we would just simply create a new longer array. We copy over all of its elements into the longer one. But does anybody see any issues with me doing that? Any issues at all? Are there any issues? Say, for example, if I have an array of length, say 4, and I double it to be a length 8. And suppose that my hash function depends, like if it's like h of k is, say, k mod whatever the table size is. So are there going to be any problems if I have things just sitting around in all of these? Can I just straight up just copy them? No, right? Exactly. I can't just do that. This is what brings me to the idea of rehash. So what I mean by rehashing the table means you're going to go through all of the records in your original table. You're going to go through each one of them. So you're going to traverse through all of the table. So you're going to go through each one of the linked lists. You're going to look up its record. You're going to look at its key. You're going to insert that into the new table using your hash function. So for example, and the main reason why we have to do this, by the way, is remember if I have something like the key is, say, 16, for example, if the table was size 4, it would be right here. But 16 also, in happenstance, also happens to be slot 0 also in this table of 8. But suppose I give you, say, the key is 17. 17, okay. It may be the case, yeah, sure, it'll be in slot position 1, sure. But what happens if something is in position 4 that should actually be somewhere else in this table? Well, this is why we have to apply the hash function to reinsert every single one of them. This is what it means by rehash. So that's what, if somebody asks you, oh, I need to rehash the table, it means that you have to recreate the entire table. And from your intuition of this so far, is this a cheap operation or an expensive operation to perform? Is it cheap or expensive? Yeah, it's quite expensive. If the dictionary is really big and it's using the hash table, it may be the case you may have thousands upon thousands of records in this table. That means you're going to have to go through everything and reconstruct the whole table, which that takes time. That's definitely going to take a while, depending on how big it is. Keep in mind, we're talking if we're talking about thousands, we're still dealing with things that are really fast still for us from our perspective. But you also got to keep in mind that this could have millions of records in it. It'll start making a difference between, hey, look, maybe I should have picked a different constant, or I should have thought about the load factor a little differently. So very often, what you'll do is you'll come up with some ideal idea for what the load factor should be for your table by reverse engineering this formula. So for example, if you want the load factor to be 0.75, you just say, okay, well, the number of records I'm going to have in my table, if you know this in advance, it's even better. Okay, you know how many you're going to have. You can reverse engineer this equation to tell you what the size of the table should be. If you can do that, you're good luck, right? So this is one way you can avoid having to rehash the entire table, but also get an idea for what the load factor should be. So are there any questions about that? So this is something I wanted to bring up so that you know, okay, so what exactly does this load factor do for me? It gives you some insight into the relationship between how long these lists can get on average. But at the same time, it gives you an idea when the performance might start degrading, when this load factor might start getting a little gets a little crazier. So you may think of the load factor as just a constant. So you want to keep it so it's some constant as opposed to it being something that might be scaling quite erratically. You'll see this very quickly, by the way. If you ever try implementing this, you'll be implementing something like this on the last assignment. Try it where you only have one list versus, say, 10,000 lists. And you'll see that the performance is considerably different. You'll see that it just degrades right back to the things we were talking about a couple lectures ago. But anyways, are there any other questions about separate chaining before we talk about our next collision resolution policies? So remember, the whole idea here is if I have a collision happen, I'm just going to use more memory to occupy that slot. So I'm just going to stack my friends on top of each other. It's not very pleasant, by the way, to do that to your friends, but we could do that with our linked lists. Okay. So if we're okay, I want to shift gears to our next collision resolution policy set. We have two more that we're going to talk about. Through how much time, we'll see how far along we get today. The next policy I want to talk about is something called open addressing. So it's actually a collection of different policies, and they all are built around one central idea. So I'm going to show you a couple of them, but I must stress that there's more of these that are out there. But they're all based on the same fundamental idea. So you know how earlier I was talking about, oh, well, a drawback of separate chaining is you may use too much memory. So you're at the mercy of the collisions that happen. Because every time you're gonna use more memory if a collision happens. Well, suppose that I just only use the table itself. I have M slots. I'm just gonna only use that table spot. I just don't want to use anything else. This brings me to the idea of what we call open addressing. Open addressing. So what we're going to do here is I'm always going to assume that n is less than capital M. So note that, of course, if n is equal to M, then you might rehash the whole table. So that means you're just going to make a longer array. You're going to reinsert all of the records. So that's one thing you have to keep in mind, is that I always have to ensure that there's space for my records in this hash table. I'm confining myself into the size of the hash table. So I would need to find some consistent way to deal with these collisions, though, because remember, we're still dealing with the same situation. Suppose I have my friend, they go into the bin, and have another friend, maybe goes into another bin. But the minute I have it where two hash to the exact same position, say my seal friend here, oh no, sorry, I'm having way too much fun here. If I hash the same position, well, since I'm using only the table, this is why, by the way, we call it open addressing. You can think of separate chaining like closed addressing, where I literally use the same addresses. Open addressing means that I have my addresses, but open means that I'm allowed to use other slots to insert my records. That's the why we call it open as opposed to closed. So anyway, so if I have this right here, well, I can't stack my friends, right? In this policy, it's not friendly to stacking my friends, okay? So what's going to happen instead is we're going to be trying to use the idea that as long as I maintain a consistent way of inserting, searching, and removing in my table, this is going to be something we're going to call a probing sequence. Whenever I run into a place where I get a collision, I'm going to use the probing sequence to tell me where to put my record if that happens. And if there's a collision that happens there, then I keep applying the so-called probing sequence. So for example, I see a spot right here, I'll put my friend in there. But let's talk about this. So likewise, one other detail I'm going to assume as well. Assume as well that T has for all its slots null. Finally, let's talk about the idea here. So here's the idea. So check position T sub h of k. If null is there, you can insert the record into this slot. So you just literally just assign that position to your record. So the pointer to your record. Now, there's a problem, right? Like my example with my seal. However, if T sub h of k, if T sub h of k has already a record, meaning it's not null, use a probing sequence which I'm going to define what that is shortly, to tell us where to check for a spot next. So we're going to explore two different ways of doing this in this course. The first one's going to be linear probing, which we're going to talk about shortly here. Linear probing. The second one's going to be double hashing, which deals with a couple of things that will improve the linear probing process. So the collision resolution for both of these, regardless, collision resolution is probe to find the next available spot. The next available spot of T using a probing sequence, which I'm going to define that a little bit more carefully here shortly. So far we're doing okay. So I'm going to just have the table itself. And then what I'm going to do is I'm just going to put the records in this table. But the thing is, we're going to have collisions like we talked about initially, right? So rather than just building lists, I'm going to actually have to find a spot to put them in. So I'm going to have to do this consistently. The consistency comes from this idea of a probing sequence. So what's going to happen is, just like if I was a bunny, I'm going to make hops. So if ever I have it where I come to a slot and it is occupied, I'm going to hop over to the next spot that the probing sequence tells me where to check. Then I check if that spot's available. If it isn't, then I hop to the next available spot and I check if that is available. If it isn't, then I hop to the next position and so on. This is what the probing sequence will do. It just tells me which slot should I check next. If I run into a spot where it is available, I insert it right there. If I run out of ability to check all the slots, like if I check every slot by the end of this process, then I know there's no place to put it, it's full. Or even better than this, it also will allow me to just keep hopping along until I eventually maybe find a duplicate if I'm trying to do an insertion, for example. So think of it like a bunny rabbit. Imagine me as a really, really big bunny, like just there. I'm the bunny rabbit. I'm going to go for my hopping around. Say it's a little bit early for Easter, but well, technically it's late for Easter, but you can imagine me as the Easter bunny. But yeah, so that's what we're going to be doing here. So let's just start talking about linear probing. Well, as soon as you see it for linear probing, you pretty much got the main idea for how you do this. So let's talk about linear probing. Okay, so let's talk about linear probing. So on a collision, check the next successive. So it means the next one that follows. Successive position, mod capital M, the table size, until a spot to put the record is found. So here's what the probing sequence will look like. So you start off with checking h of k. So you check h of k first. If it's there, you insert it. Otherwise, you're going to apply the next one we're going to have here. Then you apply h of k plus 1 mod capital M. If you get a failure to insert here, then you try h of k plus 2 mod capital M. And then, of course, after that, if you get a failure to insert, then you get h of k plus 3 mod M. And you just keep doing this. Often in practice, you'll find that when you pick the table size for linear probing, you normally just presume it's something like a prime number. It doesn't have to be, though. I will be showing you the other open addressing scheme that I do have here. That one will actually require that the table size is a prime number. I'll talk more about that depending on how far along we get today. So let's talk a little bit about this. So I thought what we would do, because I have actually the pseudocode for this in here, but I think that you'll get the idea pretty quickly if we just start diving into some examples. So when you do a get operation, you apply the probe sequence. So you just follow until k is found. And of course you return null if null is encountered. Because keep in mind, you might hop over to a spot that has null in it, which would imply that nothing was inserted there. Which means that where you did hop would be where what you're looking for would be. Is encountered. Or all of t is checked. So it means you checked either the whole table or you ran into a null. That's all get does. So I will let you take a look at the pseudocode in the notes. So just take a look at the notes for the pseudocode here. I must stress that again, you're going to see very quickly that we're going to have a very similar setup to our previous one. I thought what we would do is I would just give you an idea for how this works. So just remember, the whole idea here is imagine me as the big bunny. And I'm going to examine the first spot that I get is h of k. If I do not find it there, I will proceed to hop to the next spot over. So I will hop to my right to the next spot, right? And if I don't see it there, I hop to the next spot. And I wrap around the table if necessary. But if I hit a null, that means nothing's there. It means that the bunny fell into a hole. So what I'm going to do is I'm going to perform some insertions first, so you can get a flavor for how this works. Because the algorithm for put and remove is very similar to this idea. So why don't we just dive right into this. Just dive right in. Let's get on this. So let's draw out a table. So I'm going to make a table that has 9 slots in it. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to have the table size is 9. This is my table T. I'm going to have 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to do a whole bunch of insertions into this table so that you can get a flavor for how this works. So here are the things I'm going to insert. We're going to start off with 18, then we'll do 16, then we'll do 8, then we'll do 44, then we'll do 3. That 3 is looking a little sad. Let's fix that. 3, 1, and then 19. So my hash function I'm going to use is h of k is k mod 9. K mod 9. And let's do this. So I'm going to presume all of these are null initially, just for the sake of saving your hands some time. So 18 mod 9, what slot does that go into? Where should I start? What slot does 18 mod 9 tell me to go to? 0. Yeah, very good, very good. So notice that this is null, so I can safely insert. Right? Okay, now we go to 16. What slot should 16 go into? Yeah, position number 7. Now, for an easy way to check this, well, 18's in 0, 17 would be 8, 16 would be 7. So if I unwind it by subtracting by 2, there it is. So notice so far we're doing okay, right? This looks pretty awesome. 16, V2. Next, which slot should I go for next? 8. Yeah, see. Let's put 8 in here. Okay, now 44. Now, let's see. 44. So, where should it go? Let's start off with that question. Where should, before we think about linear probing, which slot should 44 go into? Yeah, so far, let's see, I'm just seeing what we got. We got 8. So far we got 8. Well, let's think of it. Well, let's see. 9 times 5 is 45, right? So that means that one less than that would be 44. So yeah, so it looks like we should be right here, right? So we have a collision that happens at position 8. So there's a collision. So for the 44, we have a collision at position 44 mod 9, which is just 8, right? So now, this is where I get to put my bunny sense on. Well, I'm at position 8. I'm going to now jump 1 to the right, and I'm going to examine that spot. Well, look. Going to the next spot is going back around up here. I check that position. So we're going to try 8 plus 1 mod 9, which is just 0, right? But do I get a collision again? Because keep in mind, I am down here. I'm going to hop up to here. Yes, I got another collision. So I'm just going to write oops. Oops. So let's try another one. Let's try the next probe. So we're going to hop. Remember, just think of the bunny. So I'm going to try 8 plus 2 mod 9, which is position 1. Oh, look. Position 1 there is available. So I'm just going to place that right there. So just before we get to our next insertion, I just want to show you the idea behind this. So if ever I need to get 44, a hash function would tell me to go right here. I can check if that's 44, right? It's not 44, so I apply the probing sequence. It will tell me, hey, look, check the next one. 44 is not here, right? So then I check the next one. 44 is right here. I can return the value of that. So notice that this probing sequence can be consistently used for insertions and retrieving. But the idea is that this probing sequence has to be maintained or else we might lose track of records. This is why we have to be consistent when we do this. So next, let's try 3. Well, 3 is really easy. It's right here, right? So I'm just going to put in 3 here. 3v5. Okay. Everybody, where should 1 go after I apply the probing sequence? So where should it go? Like if I do the probing sequence, what position will it land in? So imagine me as the bunny. Yes, I'll go into position number 2 because I will hash to this position. I see something's already there. I'm going to hop to the next spot. And I see I put a 1 in here because it's available to me. Exactly. Is everybody getting the idea of this? So the idea is that whenever I don't have a spot available, I hop to the next spot and I try there. So let's see 19. Okay. So we know 18 would be position 0. So 19 would be position 1. So notice that I'm going to get a collision right here. So when I try doing 19, I'm going to try right here. Oh, that doesn't work. Well, that doesn't work. And that means I'm going to hop one more time. And look, this one's free. I can go 19 and put that right here. So notice here that we might have to make several hops. Does everybody see that? Is that we might actually have to do many hops. Like this could happen. But under our uniformity assumptions, it should be the case that these hops or chains of hops, so imagine a sequence of hops that I would perform that takes me to each successive spot that gets me to where I need to look. If the uniformity assumption that I have is in place, on average, you should expect me to pretty much just land right on it, right? But the thing is in the worst case, that doesn't necessarily happen, right? Could somebody tell me a worst case scenario for example, getting? Like if I want to perform the get operation. What might happen? What might happen? So suppose, just to make it a little easier for you to see, suppose that my table is pretty much full. And suppose that I'm looking for something, but is it something that will be in the table or not in the table? Well, I'll give you a bit of a tip. Do you remember that we had that example where I had like the multiples of 7? Well, imagine I give you multiples of 9. And imagine I could just fill this whole table up with multiples of 9 by creating these probing sequences. Well, I use the probing sequence to end up with a chain of hops like this. Well, I can have that happen for an insertion. I can also have it happen where I fill up almost the entire table just doing this. So it means that when I'm doing insertions and searching and so on, in the worst case, you're going to end up still with big O of n. But on average, you should expect it to be big O of 1. Just the same thing, just the difference is now we're governed, instead of it being by a length of a list, it's governed by the number of hops I'm going to have to do. So now, the worst thing that can happen is that these chain of hops that I do, imagine this is a really busy bunny that has to go all the way down, all the way through this entire thing. Well, it may go through the entire thing, right? So just keep in mind that if you're thinking about doing the insertions and the removals in this process, that these are all going to end up being the same. It's going to be the same complexities we had before. So give me one moment here. I just want to make sure I don't lose track of where we are. So the big thing here is that you can go through the analysis just like we did. If you take a look at the pseudocode. So if we think about get, for example. So if you take a look at that pseudocode, I'll have the full analysis there. You'll see that in the worst case, you'll again get big O of n because of the reasons we've just discussed here. On average, again, it's big O of 1. But remember, the load factor never exceeds 1 in this case because we have to use the slots in the table, right? So that's one way you can easily see that just because the hop lengths, well, because on average they'll land in spots where they don't collide, right? So on average, under our uniformity assumption, you should expect on average to be constant time. But now the difference here versus the separate chaining is that we're actually using the table itself. So we're not technically using extra memory other than what we actually are using just for the table itself. So note that this is also true for put. So if you want more details for these two, just take a look in the notes, because I do have the pseudocode for both of these in the notes. So just take a look at the notes if you want more details on these two. So I wanted to make a remark about removal before next day we'll talk about double hashing and kind of the drawbacks of linear probing. I wanted to mention one small detail about removing. So do you remember that when I do this probing sequence, when I, for example, follow the probing sequence, it should be able to get me to where I need to be so that I can hop successfully to the right spot. Now suppose, just for the sake of discussion, that say I removed 3. I haven't told you how I'm doing it. All you know is that if I want to find 3, I could just hash the position 3. If it doesn't match the one I wanted to remove, I can just hop to the next position successively until I find it, right? So that's what you would do for removal. But suppose I do that and I get rid of 3 and say now this is just null right here. Suppose I was looking for 19. Suppose I was looking for 19. Well, 19 will start me here. Then I hop, right? I hop. Then I hop. But there's a null here. I fell in a hole, right? Can I get right here? Well, I'm in a hole, right? I can't hop over there. I can't. I've lost track of 19. Does everybody see that? Because there's a null right here. So that's a problem, right? Because remember, we need to be consistent about this. If I'm doing insertions and searching and stuff, and when I encounter a null, that means simply there's nothing there, right? So in the context of searching, it means it doesn't exist. In insertion, it means you could safely put it there. So if I were to straight up remove that record like this and leave null there, we're going to have a problem. So there's this idea that actually exists when we do the removals. So when we do remove, we just apply the probe sequence. So you just follow the sequence until key K is found. And we're going to make use of a very crafty trick that's used in a lot of very subtle places where you have tables, like lookup tables and things like that. This is actually done in some systems applications, such as things like caches, for example. Like, have you ever heard of a cache before? It uses a trick kind of like this as well, where you flag slots for deletion, but you don't delete them until it's necessary. So, found and mark the slot with a tag I'll call delete if exists. If exists. So you just report an error otherwise, so meaning that you fail to remove it. So I must stress that the analysis for this algorithm is just like those two. So the analysis is just like this as well. So remove is just like these 3. So it's going to match up with the same worst and average case time complexity you had for separate chaining. So just to be very clear, what we're going to do is we're going to make use of an idea that's it's often called a tombstone or a marker. What we're going to do is we're going to do what is called lazy deletion. So this is the idea. So this is what we call lazy deletion. Some people call it tombstoning. where you use a tombstone. So this is what we call lazy deletion. It's like often a crafty trick. So if ever you need to delete stuff and you need to act still like it exists, what you do is you create something that isn't null. You put it there, but the point is that delete is not equal to null, but it's not equal to any of the keys. So the point is being big-brained here, delete is not null. It is just another value that is not present anywhere else in the table or any one of the keys. It could be a label, for example, or just some flag, for example. So the idea is that now, because this is in fact not null, right? So that means it will allow you to hop over to 19, which fixes our issue. So there's two options you really have with removal in the scheme that we have. What you do is you just simply mark them for deletion. And then after, if this table becomes full, you can rehash it and ignore all of these delete ones, all the delete labels. So that's what we would commonly do in practice if this thing gets full. But notice very quickly, if you do a lot of deletions, you're going to be wasting a lot of space in this table. We'll talk more about that next time. When we come back, we'll start talking about double hashings. So please take a look at the notes for the pseudocode for these operations, and I'll see you next day, okay, everybody? So I say thank you very much, and have yourself a beautiful day. I'll see you later.